In this module, we introduce a physical quantity called Gibbs energy and describe its properties. We have shown before that the criteria of spontaneity or reversibility for a closed system can be formulated as follows. The change in entropy of the system plus the change in entropy of the surroundings must always be greater than or equal to zero. However, it can be challenging to calculate the entropy change in the surroundings. We want to be able to determine if a process occurs without having to consider the entropy changes in the surroundings. We don't want to calculate the entropy change in the surroundings, but it does not mean that we ignore it. We limit the surroundings role to keeping constant certain system variables such as temperature, volume, or pressure. To formulate alternative criteria of spontaneity or reversibility for a closed system kept at constant temperature and pressure, we introduce a new extensive state function called Gibbs energy G. It is defined as enthalpy minus the product of temperature T and entropy S, which is also equal to internal energy plus the product of pressure P and volume V minus the product of temperature T and entropy S. It has following properties. In a closed system at constant pressure and temperature, the equilibrium state corresponds to the minimum of Gibbs energy G. Specifically, under these conditions, Gibbs energy decreases during a spontaneous process and remains constant during a reversible process. Now you might be wondering, in a closed system at constant pressure and temperature, what else can change? You are right to question this, as we often don't consider other interactions in the system. Let's look at the fundamental equation of thermodynamics expressed in terms of Gibbs energy. When pressure and temperature are constant, the only parameters that can change are those related to what we call non-volume work. This implies that even while maintaining constant pressure and temperature, there might still be some known or unknown internal processes within the system. Examples of such processes include chemical reactions or the mixing of substances. Let's refer to coordinates describing these processes as internal variables. If we examine the Gibbs energy at constant temperature and pressure as a function of internal variable, a spontaneous process is characterized by a decrease in Gibbs energy from point 1 to point 2. When the Gibbs energy reaches a minimum at state 2, the system is in equilibrium. More precisely, the criteria for spontaneity or reversibility for a closed system at constant pressure and temperature can be expressed using Gibbs energy and non-volume work as follows. The differential of G during a process at constant pressure and temperature is less than or equal to the non-volume work performed during the corresponding state change. Here, equality signifies a reversible process, while inequality points to an irreversible one. When no non-volume work is present, G can only decrease or remain constant, as introduced earlier, but there is more to this. Now, consider the finite change of G during a state change from 1 to 2 and the corresponding non-volume work. This scenario leads us to the following relationship. The change in Gibbs energy at constant pressure and temperature is less than or equal to the non-volume work performed during this state change. An important point to remember is that since Gibbs energy is a state function, the temperature and pressure have to be the same only at the beginning and at the end of the state change. What happens in between is irrelevant. So, the non-volume work performed in a process leading from state 1 to state 2 cannot be less than the difference in Gibbs energy between these states. Given that useful work is negative, we conclude that the decrease in Gibbs energy represents the maximum useful non-volume work a system can perform during a state change at constant pressure and temperature. On the other hand, positive work done on the system may increase its Gibbs energy, though this scenario is of lesser interest. Let's consider the example of electric work. Imagine adding metallic zinc to a copper ion solution. The initial state of the system is copper ions and metallic zinc. A chemical reaction occurs at constant temperature and pressure where zinc is oxidized and copper is reduced. Once equilibrium is established, the system mostly contains metallic copper and zinc ions. If this process runs spontaneously, the entire decrease in Gibbs energy is dissipated as heat into the surroundings. Now imagine that we have constructed an electrochemical cell instead. The available decrease of Gibbs energy between these two states is utilized as cell potential in the cell. The maximum available cell potential, E, is proportional to the decrease in Gibbs energy. In both scenarios, we transition between exactly the same states, and the Gibbs energy of the system decreases by the same amount. The difference lies in how we use the decrease in Gibbs energy, either letting it dissipate or utilizing it to perform useful work. So, a closed system at constant temperature and pressure inherently aims to minimize its Gibbs energy G. Using the definition of Gibbs energy, its change at constant temperature delta G can be expressed as the change of enthalpy delta H minus temperature times the change of entropy delta S. For a state change to be spontaneous, delta G must be negative. Here we can identify two contributions: enthalpic delta H and entropic T delta S to the change in Gibbs energy. A process is always spontaneous when the enthalpy change is negative and the entropy increases. Under these conditions, negative enthalpy change corresponds to energy being released as heat during the process, which is characteristic for exothermic processes. Conversely, a process is never spontaneous when the enthalpy change is positive and the entropy decreases. This enthalpy change represents absorption of energy as heat during the process, indicative of an endothermic process. In other cases, the exact relation between delta H and T delta S determines the spontaneity of the process. If both the enthalpy change delta H and the entropy change delta S are negative, the process is favored at lower temperatures. When the temperature is sufficiently small, the contribution of the positive term minus T times delta S could be less positive than the value of the negative enthalpy change, delta H. Conversely, if both delta H and delta S are positive, the process is more favored at higher temperatures. In this scenario, the negative term minus T times delta S can overcome the positive enthalpy change if the temperature is sufficiently high, pushing delta G to be negative and making the process spontaneous. It's important to note that equilibrium, indicated in this case by a minimum of Gibbs energy G, is a delicate balance. It corresponds to a compromise between achieving minimal energy and maximizing entropy. In most cases, the system needs to balance these factors to reach a state of equilibrium.